All right, here's 2010 Form B. The question is right here. So the first part says find the interval of convergence. In B says we need to look at showing that this is the solution to this differential equation. Okay. Part A, very fair. It's worth 5 of the 9 points. Kind of expect everyone to get this one right. Finding the interval of convergence is just we're going to look at the ratio test and then we have to analyze the endpoints. Let's attack that problem first. Okay, so here's f of x and we want to find the interval of convergence, which means we want to do the ratio test. The ratio test has us look at the limit of a to the n plus 1 over a to the n as n goes to infinity. So we're going to look at negative 1 to the n plus 1, 2x to the n plus 1, over adding 1 to n minus 1 just gives you n, all over negative 1 to the n, 2x to the n over n minus 1, and we're going to look at that limit as n goes to infinity. So L'Hopital says that we can do that, right? The limit of n and n plus, or excuse me, n and n minus 1 as n goes to infinity is equal to 1. This guy and this guy, that just gives us a negative 1. And that's an extra 2x factor. So then you really just get your limit to be negative 2x. I'm going to make the argument that that negative is worthless, and the negative is also very predictable. This is an alternating series. So of course, if you looked at the next term versus the previous term, you're going to get a negative. They're alternating, right? It goes plus, minus, plus, minus, plus, minus. So it doesn't matter where in the sequence you look. The next biggest term versus the previous term, the ratio has to be a negative. By that ratio, it doesn't matter. And again, I'm going to show you that. You can just drop it. You can trust me after you see this that it doesn't really matter. Right? So let's say you set negative 2x in between negative 1 and 1. Well, go ahead and divide everything by negative 2. You're going to make that positive a half. You're going to have to flip the inequality sign, flip that inequality sign, and then 1 divided by negative 2 is negative 1 half. And then you get this result. X is less than a half and greater than negative 1 half. Now, it's kind of silly how we write that. It's way easier if you just would listen and say, you know what? That negative clearly doesn't matter. It doesn't matter whether you set negative 2x in between negative 1 or just 2x in between negative 1. Dividing by 2 here gets you the same thing, right? These are equivalent statements. This is kind of more reading things left to right, and this is kind of going backwards. But they're the same. So it doesn't matter that that negative sign's there, so it doesn't matter that the alternating even is in that problem. Okay, now we need to look at endpoints. So if x is actually equal to a half, it gives us a specific series. So plug x of a half in here. 2 times a half is 1. 1 to the n is 1. So just get rid of that. And so when x is a half, you specifically are looking at the series, the alternating 1 over n minus 1. And we know that this converges based on the alternating series test. And so, bingo, we want to include that value. However, if x is negative half, the other endpoint, you get negative 1 to the n. 2 times negative half is another negative 1 to the n. But those cancel each other. When I say cancel, I mean negative 1 to the n times negative 1 to the n is negative 1 to the 2n, which is just equal to 1. And so that produces this series, 1 over n minus 1, not alternating. That diverges based on the p-series, so we do not want to include that. And so we get that as our interval of convergence. Again, you got to look at both endpoints. Half makes it alternate, negative half doesn't make it alternate. Since it's just an n, it doesn't have absolute convergence. Only the alternating version converges, so we want to include that. Ratio test is, gosh, I can't think of a problem where we don't use the ratio test when we're looking to find the interval of convergence. All right, now we got the tricky one. And if you just kind of go through this slow, then it'll make some sense. Okay, so let's write down the function again. The function f of x is given by the summation 2 to infinity of negative 1 to the n, 2x to the n over n minus 1. And what we want to show is we want to show that x, y prime minus y is equal to what appears to be some random function, 4x squared over 1 plus 2x. Anytime you want to show something, it's kind of like a trig identity where you really sometimes can work with both sides, but in this case, we're just going to work with this left side and show that this left side is equal to this. So Don't mess with this at all. Don't even think about it. We're going to just do this. Okay, so first, let's find y. Again, y is just the function, so let's find what it is. So when n equals to 2, this is negative 1 squared, so that's just 1. 2x squared, so that's 4x squared over 2 minus 1, so that's just 4x squared. Okay, and now plug in n equals to 3. This makes it a minus. N equals to 3 makes this 2x cubed, so that's 8x cubed over 3 minus 1. So 8x cubed over 2 is 4x cubed. All right, and let's just do one more. 3 is usually pretty good. Plus, because now when I plug in n equals to 4, that's there, and that's 16x to the 4th over 3. So 16 thirds x to the 4th minus blah, blah, blah. Okay? And if I'm interested in looking at this, I need to know y, which I now know, and I know y prime. So let's take the derivative. So that's 8x minus 12x squared plus 64 thirds x cubed minus blah, blah, blah. And now let's just do what this says. This says take x times y prime minus y. That's what we're working with here, okay? So what happens if I take x times y prime? I'm just taking x times all of these things. So that's 8x squared minus 12x cubed plus 64 thirds x to the 4th minus blah, blah, blah minus my y values. 4x squared minus 4x cubed plus 16 thirds x to the 4th minus blah, blah, blah. Okay, and I'm just working with this guy, and I'm going to show that it's equal to that. Okay, this is an infinite polynomial minus another infinite polynomial, which is fine. Don't worry about the infinity. You're just going to combine like terms. So 8x squared minus 4x squared is 4x squared. Minus 12x cubed minus 4x cubed, that's plus 4x cubed, minus 12x cubed plus that is minus 8x cubed. And this one's the nice one. It does work out. I know it looked like this was gross at first, but it'll work out. 64 thirds x to the 4th minus 16 thirds x to the 4th is 48. Just write that up here. 64 thirds minus 16 thirds is 48 thirds, which is just 16. So you got 16 x to the 4th. And then all these other terms are going to combine, but let's not even worry about those. So that's what this is. Right? And our whole goal is to show that this side equals 4x squared over 1 plus 2x. But check it out. This is a geometric series. This is an infinite polynomial that we know what it is. Look, a is 4x squared. R, remember r is our multiplier. Look what r is. What do you do to go from here to here? It's just a minus 2x. Boom, boom, boom. And if you needed more patterns, then you just needed to write more here. You'd get more terms and you'd be able to see it. But 3 is usually enough to go from here to here to here. Look, I get one more x. And I keep switching signs. And I go up by 2. That's what r of negative 2x is. And so we know that this infinite polynomial equals a over 1 minus r. Bingo. And now I've gotten it. I've shown that xy prime minus y equals this because I showed that xy prime minus y is this infinite polynomial, and I know using Taylor series that this infinite polynomial equals this function, and so boom, I showed that this is a solution to this differential equation.